Welcome to qnawire.
Question we want to consider the fusion reaction for hydrogen atoms into a helium atom and a neutron. So we want to calculate the energy by calculating the electrostatic potential when they touch. So this we need to use the Coulomb energy. So the radius of a hydrogen atom can be found the very first equation of this chapter. We can have this and then 2 1/3. So this, remember, this is a constant, and this is or like the total weight in terms of atomic numbers to the 1/3. So this is going to give us the rate of this atom, which is 1.51 times 10 to the negative 15 meter. When the two atoms touch, they really are two radiuses apart, but we're going to assume that some part of it is going to overlap and they are 1 radius apart. So the electrostatic energy is going to be 1.4 pi epsilon naught E squared over R. This is just a constant. This is electron 1.10 to the negative 19 radius we found in that case. I use 2 radiuses because when they touch, they are 2 radiuses apart. So this is going to be 9 times 10 to the 9th Newton meter squared over C squared times the electron is 1.6 times 10 to the negative 19 Coulomb squared over 2 times the radius is 1.51 times 10 to the negative 15 meter. So to give us an energy of 7.65 times 10 to the negative 14 joule. In terms of EV, it's 0.48 MeV. That is for part A. And then we can look at part B. Part B wants us to look at the energy liberated in this reaction in MeV and then in joules. So in this case, we need to calculate the change of mass. So delta M is going to be the mass, 2 times the mass of hydrogen, subtract the mass of helium, the mass of nitrogen. This mass is going to be 3.510 times 10 to the negative 3 U. So this corresponds, and we know each U is 931.5 MeV. If we use this conversion factor, 3.10 times 10 to the negative 3 U times 931.5 MeV per U, we're going to see that the total number of energy, the total amount of energy that is produced is 3.270 MeV. So that is for part. And I think it does not ask us to compute. Oh, it also asks us to compute this in joule. So if we convert MeV to joule, we find that 3.270 MeV is equivalent to 5.239 times 10 to the negative 13 joule. Very last part asks us to find the energy per mole, and we need to remember that this gas is diatomic. So each molecule actually contains 2 atoms. And then we want to compare this energy to the combustion of hydrogen. So let us compute the amount of energy per mole. So for each reaction, we have 2 hydrogen nucleus. So each mole of deuterium has 6.022 times 10 to the 23 or this Avogadro's constant, that many molecules, then that have that many pairs, that's the same number of pairs of molecules. So we will have 6.022 times 10 to the 20 reactions for each mole of deuterium, because, well, deuterium has 2 atoms, and then 2 atoms form a reaction. So, and then each of pair reduce amount of energy of what we found, 5.39 times 10 to the negative 13 joule. So more were produced 3.155 times 10 to the 11 joule per mole. Also per mole. And we can see this is more than 1,000,000 times larger than the energy we get from the combustion of a mole of hydrogen gas.